Hey there! Let's talk about the complex number system. And the key number here to think about, or letter, if you will, is the letter I. It's a key concept here because I is an imaginary number, and that's what it stands for. Because I equals the square root of -1. You might be thinking, the square root of -1 is nothing. Well, that's what we're going to learn today, that the square root of -1 actually gets you into the playing field of imaginary numbers. In other words, they're also called complex numbers, or also types of numbers that can't be defined with any integer values like 3, 5, -3, not even 5. So let's get started. So, the properties of I is that it's square root of -1. Some other key facts you need to know is that I squared, which is the square root of -1 squared, is -1, just like any other square roots. When you square a square root, it just becomes the number inside it. The next thing you need to know is that I to the third power, which is also I squared times I, is -1, which is right here, times square root of -1, which gets you negative square root 1. Still, if you're still catching up here, let's talk about one more, I to the fourth, which is I squared times I squared, which is right here, -1 times -1, which equals 1. So let's kind of wrap this up here. I equals square root of -1, I squared equals -1, I to the third power equals negative square root -1, and I to the fourth power equals 1. If you kind of look at these, square root of 1, -1, and negative square root of 1, so I and I to the third power are related because they're like inverses. And same thing with these two, they're just inverses as well. Alright, let's move on to some more complicated things. I still have the basic things right here. So let's add these complex numbers. And complex numbers are made out of a minus bi. So with one real number subtracted by one imaginary / real number, complex. It's just like adding any other thing. So we would have 4 plus 3i plus 3 minus 2i. We can just remove the parentheses here and get 4 plus 3i plus 3 minus 2i. Combine like terms because you cannot combine a real and a complex number, and we would get 7 plus I. And that would be our final answer. And make sure it's always in this form too, because that is the proper syntax. So for same thing for negatives, don't forget to distribute this to each side. And 3 minus I minus 4 minus I equals -1 minus 2I. Let's move on here. Now it's getting a little more complicated because if you remember from polynomials, if we are going to multiply, we have to multiply using FOIL, such as this, 3x plus 2 and 3x minus 2. We'd have to multiply it out with FOIL, and same thing here, except we have a little issue that we'll get to. So 2 times 4, 2 times 3i, -I times 4, and -I times 3i. Let's multiply it out. So 2 times 4 is 8. 2 times 3i is just 6i, just like standard multiplying. -I times 4 is -4i, and what do we have here? We have -I times 3i. So we're at a kind of a roadblock here. What is 3i times I? Well, that's 3i squared. Well, what is 3i squared? Let's look back to our properties here. 3i squared would be, well, it has I squared. And what is I squared? I squared is negative 1. So it's pretty much 3 times negative 1, which is negative 3. So let's rewrite this now. 8 plus 6i minus 4i minus 3. So this is just plus 3. And now the final answer we have is 8 plus 3 is 11 plus 6i minus 4i plus 2i. Let's try this one more time. In this problem, just FOIL, and let's have 3 times 5 is 15. 3 times I is plus 3i. Negative 2i times 5 is negative 10i. And negative 2i plus times positive I is, let's write it out here, 2i times I, which is 2i squared, which is 2 times negative 1, which is negative 2, and 15 minus 7i minus negative 2, so plus 2. Be careful with your negatives and positives. Those are the most common reason why people make mistakes on these. So the final answer would be 17 minus 7i. So if we wanted to graph complex numbers, there's a specific graph that we have to use. It's not like a standard graph. So for the x-axis, we would have the real number axis. This is only for numbers like 1, 2, 3, 4, any integer number or decimal, any number that can be written with a, so like 3, even pi, even irrational numbers. And for the bi, that would actually be the imaginary axis. And why we have an imaginary axis is because of I. So we'd have bi up here. So if we wanted to graph this, let's say we have, 3 plus 2i. We see the 3, so let's make 1, 2, 3. We know it has to be on this axis right here. The way how we can find its y-axis is it goes up as I, 2i, 3i, and so on. So since it's 2i, it would meet up on this axis. So the number would be located right here. And we can get into vectors later on, but that's how it would look like. Let's try one more. Let's try this out. So 5 minus 2i. So I'll kind of slow down so you can think about it, but so we have negative 2i here, and we have 5 up here. So it would connect to be right there. Alright, there's one more thing we have to talk about, and it's the thing that you typically find when you solve a polynomial identity and it says no solution. Yeah, we're talking about the positive sums of two polynomials. Let's say, you know that 4x squared minus 25 equals the sum of the square roots, which is 2x plus 5. So we know it'd be 2x plus 5 and 2x minus 5. But what about 4x squared plus 25? Normally we would say no solution because there's no real theorem for that. But there actually is, and we can use complex numbers for that. So let's say we can use, because we know 5i times 5i is 25i squared, which is negative 25. It doesn't matter if it's positive for complex numbers. So we can do the 5i and 2 and write 2 plus 5i and 2x plus 5i and 2x minus 5i. And if we check our work, it's true, because we get 4x squared minus 10xi plus 10xi plus 25. And that's the last property of complex numbers that we can use in polynomials. Thank you for watching this video. This has been SATFreePractice.com providing you with the complex number system.